So, hello and welcome to lecture number 7 on convex analysis. Theme today is the inf-projection and the inf-convolution. And there are two warm-up questions in the chat on the topic of the last lecture, which has been continuity properties of convex functions. So apparently there are no answers now, so I don't think it makes too much sense to discuss them right now. So I'll check in later if there are any answers, and if there are answers, let's discuss them, and if not, let's wait. Okay, one more thing for the listeners of the lecture who are listening right now at production. So there's this lecture notes I upload. I try to upload right before the lecture or distribute a few days in advance. And you may notice these are kind of hot off the press, means that they contain a bunch of errors, unfortunately. Some of them are just simple typos, which is probably not too bad for you, but some of them are severe errors, less than instead of a greater than, for example, which is quite easy to type or to make a typo in that case. And please submit more errors. So I catch a few of them when I do the lecture, and then I correct them later. But for sure, I'm not going to catch everyone. So please submit more errors, and also for the benefit of the other listeners, because what I not do is each time I find an error, upload a corrected version of the lecture notes. I will do that only twice a semester, in the middle and in the end. Otherwise, there will be too many versions floating around, and we probably can't agree on which version we look in case we have to discuss something in the lecture notes. So, and once an error is submitted via std.ip in the forum, then everybody can see and check if it's really an error or not. So please do submit more errors in case you find them, but it's not that hard to find errors in my lecture notes actually right now, because it's kind of the first time they are used here. So, okay, so still no answers that I can see, so just let's start. In case you answered and it's not showing up, just drop a note. Okay, so topic of today, number 7, is about the so-called inf-projection and inf-convolution. Okay, so what's that about? First definition is, so if you have a function phi, which is now defined on the product of two real vector spaces, let's say Rg times Rm, in the extended real numbers. Any function, it's not really important if it's convex right now. Then we define as v of u the value of the infimum of phi of x and u. You take the infimum over x in the first variable, and it's Rd. And this is called epigraphical projection. But we're going to use the other term. This is inf-projection. So that's the term I want to use. So let's have a look at how this looks. So I try to do it by hand, but I think it's just simpler to have a look at the plot. So that's the graph of a function in R2. So in this example, d is 2 and m is 2. So you can just look at from different sides. So actually it's a convex function, but it doesn't matter too much. So, and what is now the inf-projection on one of the variables here? So then what you need to do here for the inf-projection is to look at the function along one direction, let's say this one, and along this direction always take the minimum value of the function you find. So here it will be a lower value, here it will be a value probably at that end, and so on. And actually it's very simple to have a look at the inf-projection just graphically. You just view it exactly from one side. So this is now really a side view where one of the coordinates is really projected out, and then the kind of the whole line down here, that would be the graph of the inf-projection. So along this direction, that's the lowest value you can see. And that also explains the name epigraphical projection, because what you really see here, so if you would fill everything above, up from above, then the epigraph of the epigraphical projection is the projection of the epigraph. So that explains the wording. And so these can look quite differently in different directions. So this is the epigraphical projection for the other coordinate. Okay, so it's not that simple to find that by hand. So this from one coordinate, and this is more or less the other coordinate here. Okay, so that's that. And so it's of course it's related to convexity. And one thing which seems obvious from the picture is that inf-projections of convex functions are convex. That's true, and that's theorem 7.2. So if phi convex, so such a phi, then V also convex. And moreover, or in particular, if you have C is an R m plus 1 convex set, then the set V of U, which is defined as the infimum over the values alpha, such that alpha and U is in the convex set, is a convex function. Okay, so this is not that hard to prove. Let's do it. So so we take two functions in the domain. So it's a convex function, extended real numbers, but we only need to consider points in the domain. So these points are pairs, x1 u1 and x2 u2 in the domain of phi, and parameter for convex combinations. And then we have, if we take the convex, or take the convex combination of the function values, x2 u2, then that's larger equal the value at the convex combination, which means lambda x1 plus 1 minus lambda x2 and lambda u1 plus 1 minus lambda u2. And so now there's one typo again in the lecture notes. So by definition of the inf-projection, that's larger than the value of v at that point. So taking the infimum over all this gives you v, and so this is one particular point, so that's clearly larger. Okay. The convexity of phi by definition of the inf-projection. Okay, now what we do is we take the infimum over on the left hand side, taking inf over x1 and x2 on the left. Shows yes. So because now the right hand side does not depend on xy and x1 and x2 anymore, so we can just take the infimum here twice over x1 and then over x2, and then this left hand side is exactly the lambda times v of u1 plus 1 minus lambda v of u2, and that's what we wanted to show. Okay, and for the last claim, second claim about the convex set, you just do consider the function phi of alpha and u is equal to alpha plus the indicator function of c at alpha and u. And if you have a close look what the inf-projection of this guy would be, so this is a convex function, it's convex plus convex if you want to see it like that, and taking the infimum, or the inf-projection of this is exactly v of u. Okay, that's that. But what else? So convexity is preserved by projections, but the rest is not so nice as you would like it to be, probably. So for example, so let's do an example where things go wrong. Example 7.3. So things go wrong with lower semi-continuity and even with properness. So let's take the function phi of x and u, two real variables, and we do it like this. We take f of x, some function f, which we can choose later on, in the domain where x, the exponential function of x, is small or equal to u, or we put it infinity otherwise. So how does it look? Let's do, so x and y are real numbers, so real variables. So let's do x here, and u, x and u. U there Okay, so where is the function not infinite? Yeah, where u is larger than x of x of x has a graph like that, and so up here the function is not finite, and down here it's plus infinity. And there we have function values f of x, so along lines like that the function has the values f of x and always the same. Okay, and let's take f of x equal to x. So here along that line we always have the function value here. So here the function value is 0, and there it gets smaller and smaller and smaller, and same here it's 0, here it's positive, and it's smaller and smaller and smaller in this direction. So and if we do now epigraphical projection onto the u coordinate, so along this direction, what do we get? So v of u is then the infimum over phi of x and u over x. Okay, so of course if now u is down here, it's plus infinity. So for all non-positive u, it's plus infinity. So we have at least two cases. If u is non-positive, we have still plus infinity. But as soon as u is positive, if you go far enough to the left, then the domain starts where the function has finite values, and the more to the left we go, the smaller they get, and it's unbounded from below, and it's actually minus infinity. So, and the thing is, this is neither proper nor lower semi-continuous. And this here, proper and LSC if f is. So this function here is a proper and lower semi-continuous function right here at the boundary. We always assume the lower value, so the function jumps up, but on the jumping point it has the lower value, and of course then here it's also LSC, so it's proper and it's finite all over here. But this one here is not. It's neither proper nor LSC. Okay, so this is not preserved, unfortunately, not under probably additional assumptions, but we're going to not go into detail about that. So that's one thing, epigraphical projection or inf-projection. So second notion, and as always, there's another notion for functions. Definition 7.4. So you have f1 and f2. Now two functions on Rd. We allow an extended valued function, and then we have the following thing. It's called f1, and then we write a box in the middle. So f1 box f2 at some value u is defined as the infimum over all decompositions of u into two numbers, x plus y equal u, so additive decomposition. And then we take f1 at the value x and f2 at the value y. And so of course, if we have this decomposition, we could also express y in terms of x, and then we would get, so y is then u minus x, and we only need to take the infimum over x, and then it's f1 of x plus f2 of u minus x. And this is called the inf-convolution. And other names are infimal convolution or epi-addition. Oops. Okay. And I'm going to use the term inf-convolution. Yeah, and actually why it's called convolution, you probably recall the notion of convolution from somewhere else. So it's related kind of to what a convolution is. So for two functions, maybe again on Rd, but no finite valued, f1 convolved with f2 at some point u. This is defined as the integral over f1 of x times f2 of u minus x dx. So that's the normal convolution. And you may notice that it's really related by formula, and it's also kind of the operations are toned down one step. So where we have a multiplication of the two functions. So of course, first we have f of x and f2 of u minus x is exactly the same. So it's also over decompositions. But where we have here a product, we have an addition down here, up there. And where we have a kind of a generalized sum, we have a generalized infimum, a minimum. So and it's kind of, so you may know that if you replace the operations addition and multiplication by minimization and addition, you get a different algebraic structure, which is does not give rise to a field but to something else. And one can do mathematics in these kind of structures. And this is kind of the replacement in the max. It's called the min plus algebra. So this looks like convolution in the min plus algebra. Okay, but this will not help us much, but it's probably interesting to note. Okay, that's that infimal convolution. And there's one more important notion about infimal convolution. So it's actually an infimum, and it's not necessary. So nobody can guarantee that it's attained. So that there has to be a value x such that this plugging x in gives the minimal value. But if infimum always attained, of course no, when it's finite, then we say the inf-convolution is exact. So that's another property of inf-convolutions. They may or may not be exact. Okay, and I see that there's one lonely answer in the chat. Okay, let's discuss then the question. So, okay, what about the first question? The convex, if the function is convex and lower semi-continuous and it's finite at some point, then it's also continuous there. Okay, so what do we know? We know that we have a convex function and we know that it's finite at some point. Let's see that. So but what may still happen, and we know it's lower semi-continuous. And convexity was actually not assumed, but anyway, that's not so important. It's assumed, okay, it's assumed. Okay, so but what may happen that the point is down here and you jumped up to infinity at some finite point. So and then at this point the function is clearly not continuous because, well, you can approach x from the right and then you have always f of x is plus infinity, but the limit has a much smaller point. So no, that's false. Okay, so what happens now if we assume that the point lies in the interior of the domain of the function, which means that there's a neighborhood here at which the function is still finite, so this cannot happen anymore, so it has to be like this, and then what the function makes over there, I just don't care because continuity is a local property. So we have a neighborhood in which is finite, and in RD we can find a compact neighborhood. So that's closing this open neighborhood here. If it's bounded, then it's compact. So then it's and then it attains maximum and minimum on that set. So it's locally bounded, and we know local boundedness implies even local Lipschitz. So this is now true. So one thing I did not really check thoroughly what happens in infinite dimensions. Infinite dimensions, I guess it's still true, but the argument is more complicated because we don't have compact neighborhoods. So I'm not sure. I guess it's still true, but it may not be true. I will check probably, but actually for this lecture we stay finite. Okay, great. Thanks for answering. In case you have any questions on the questions, please drop them in chat and we'll discuss that further if you like. So, okay, that's the infinite convolution, and it's the operation on convex functions. So one thing which is probably clear, but actually I don't discuss it. It will be okay. It comes. It looks already like it's the convexity of the convolution is pretty clear because this guy here that's the convex function. That's the convex function. No, it's not clear. It's totally not clear because infimum of convex function is not convex. So what we'll see later on that it actually is true. Okay, but first let's deal with a simpler algebraic property, and this is associativity. What about that? If we do inf-convolution twice. So first f2 with f3 and then with f1. What would we get if we do it the other way around? So okay, let's just write it out. First do the leftmost one, that's the infimum over decompositions of u and x plus y. And then we have f1 of x plus the inf-convolution of f2 and f3 of u minus x. Okay, and now we plug in this inf-convolution over here. That's then inf over x plus y equals u. F of 1 of x plus, and there's another infimum here, let's say over decompositions of sorry, I used the y formulation, so there's a y over here. So now we have to decompose y into, let's say, z plus v equals y, and then f2 of z plus f3 of v. So, and how do we deal with this? Of course, this is a constant, not depending on what we do with the infimum over here. It can just move into the infimum and then infima commute. So taking two infima over two different variables, you can do it in any order, so you can do it simultaneously. So we have the infimum over two decompositions, x plus y equals u, and z plus v equals y over f1 of x plus f2 of z plus f3 of v. And so finally we'll see that we could even get rid of one of these conditions down here, because y is z plus v, so we don't need that y. We can just put in z plus v in there, and we see that's the inf-convolution over x plus z plus v equals u, f1 of x plus f2 of z plus f3 of v. And here we see that the order did not play any role. So so it's totally symmetric in the f1, f2, f3. So, and then doing the same thing in the other direction, we will see that the same as f1 inf-convolved with f2 and then inf-convolved with f3 and then plug in u. So which means that the inf-convolution is so I did not say anything about commutative, but that's pretty clear from here. So it also commutes. F1 inf-convolved with f2 is f2 inf-convolved with f1. It's clear from the definition. Okay, so also commutative and associative, that's nice. Let's do two examples. 7.5. Let's do indicator functions first. So we have S1 and S2 sets. And then if we take the indicator function of S1 and do inf-convolution with the indicator function of S2, add some u, this gives you the infimum over the indicator function of S1 of x plus indicator function of S2 at y over x plus y equals u. So when is this finite? That's finite exactly when both of these guys are finite. So if x is in S1 and y is in S2, and if you see what this means, so it's always finite if it's not only finite, it's 0 if and only if u is of the form one element of S1 plus another element of S2. So this is exactly the indicator function of the sum of the sets. Okay, that's simple, and we don't even use convexity here. Second, so if you take f of x, for example, a norm, no matter what, could be any norm, and as f2, so f1 norm, f2 the indicator function, and c convex set. So then the inf-convolution f1 inf-convolved with f2 at u is, let's write it down, the infimum, and now we just plug it in. And we do it the other way around. So we use f1 as the second function. So we have here, and we use this formulation. So if we use f1 instead of f2 over here, then this we would have the infimum over u minus x. But we also have x, so when you use as f1, x and c. So by swapping the roles of f1 and f2, we arrive here. And what is this actually? This is just the distance of u to the set c. So it's the distance function. So if our convex set C looks like this here, as it's just an interval, then it's the function which goes up like this in one dimension. This is C, and this is just the distance here. Okay, that's that. Okay, now comes the result, which says that actually, which implies then that inf-convolutions of convex functions is in fact convex. So we do f1 and f2 are two proper functions now. Both are proper. And then we have the following inclusion, that the epigraph of f1 plus the epigraph of f2 is contained in the epigraph of the inf-convolution. So, and this also explains the name AP-addition. Not fully AP-addition, you would like to have an equality here, and that's not true in general, but equality holds if and only if, so if the inf-convolution is exact. Oops. Okay, so and this simply explains the name AP-addition. So if the if-convolution is exact, we just add the epigraphs and get a new function. And then it's pretty clear that, so this is the so if f1 and f2 are convex functions, their epigraphs are convex, so their addition is a convex set, and it's not that hard to see that it's in fact an epigraph again, so this gives you a convex function. Oh yeah, this is by exactness, this would be the case. So moreover, if f1 and f2 CVX, then f1 inf-convolved 2. Okay, that's the result. Okay, let's prove it. Okay, first we show the inclusion. So for the inclusion, yeah, we show this something from here is also contained in there. So let's take x alpha in the left-hand side, which means in AP f1 plus AP f2. What does it mean? So it means, so this is an element in the sum of two sets, which means you can decompose it into an element from here and another element from there. So this means, i.e., we have alpha I and xi in AP of fi, with the property that the x is x1 plus x2 and alpha is alpha 1 plus alpha 2, and we also have f1 of x1 plus f2 of x2 is smaller equal alpha 1 plus alpha 2, which is alpha. This is here. Actually, we have even more. We have f1 of x1 is smaller than alpha 1, and f2 of x2 is smaller than alpha 2, but we don't need that here. So what we can deduce from this is the following: the inf-projection, the inf-convolution of f1 and f2 at x is exactly the infimum over decompositions y1 plus y2 of x, f1 y1 plus f2 y2. And now comes what we now use is that x1 and x2 are also two numbers which decompose x. So this is the smallest thing we can get. So if we plug in x1 for y1 and x2 for y2, we get something which is probably larger. So f1 plus x1 plus f2 plus x2, but we already seen that this is smaller equals alpha. So and this means that the tuple x alpha is exactly in the epigraph of the inf-convolution. And that's the inclusion already. Okay, that's nice. So inclusion is done. But now what equality if and only if? So now it's going to show that the equality holds exactly when the inf-convolution is exact. So what we do now is we take a point x and alpha in the epigraph of the inf-convolution, So, and remember that means that the function value at x is smaller equals alpha. And then we use exactness. And so then assume this is exact, and you aim to prove equality here. Okay, so by exactness, we see that we can assume that the infimum is assumed, which means we have x1 so exists in x, which can be decomposed in x1 and x2, such that the inf-convolution at some x is exactly f1 of x1 plus f2 of x2. So otherwise, each decomposition just gives an upper bound for that value, but here there's one decomposition at least which gives equality. Okay, so and this is again smaller than alpha because that value has to fulfill that. So, and then what we can do now is we can consider this tuple x and alpha, and so we want to show that, so this is tuple for me, that is also in there. And this is now simpler than you think, because we decompose this as x1 plus x2, and this guy here is f1 of x1 plus alpha minus f1 of x1. So we just decomposed here, and then we just added and subtracted this guy. So we split up this tuple as this. No, comma, but a plus x2, and here alpha minus f1 of x1. Okay, and now we're going to use this inequality here to show that this is actually smaller than f2 of x2. Smaller? No, so it's the other way around. This is larger than, so it's larger than. Yep, you just subtract it one. So, which means that this is obviously a point in the epigraph of f1. And this now, because this what's written here is actually larger than the value of f2 of x2, this is here in the epigraph of f2. So in total, that's in the sum of the epigraphs. And we've shown this inclusion like this. This inclusion also, the other one always holds, so we also have this. So we have equality if we have exactness. Okay, so for the converse implication, if we have equality, then we have exactness. How does that work? So no, exact implies equality. So now for the other direction, equality implies exactness. We said f, or we denote by f the integral convolution of f1 and f2. And we assume that it's finite at some point x. So because for points where it's not finite, we don't have to consider anything. Okay. So which means that we have f of f, this tuple x, and f of x is exactly in the epigraph of f1 convolved with f2, and now we know that there's our assumption that this is the sum of the epigraphs. So which means now, so this is in the sum of these sets, we can decompose this guy into, there exists xi alpha I such that xi alpha I is in the epigraph of fi. Of course, I equals 1 and 2. And of course that you can decompose x, f of x is also missing, it's equal to x is equal to x1 alpha 1 plus x2 alpha 2. That does that equality here mean. Okay, and hence what do we get? We get f of x is then it's written here, it's equal to alpha 1 plus alpha 2, but because of this both in the epigraph, this is larger or equal to f1 of x1 plus f2 of x2. Okay, but we also have, by that, this is in the epigraph here, which is now equal to that. We also have f of x is smaller equal f of f1 of x1 plus f2 of x2. So this is by the epigraph containment like that. So we have it larger and smaller, and hence we have equality here, and which means the inf-convolution is exact. Okay, so final claim to be proven is the last one. Yeah, let's write a line on that. So it's the last one is that the inf-convolution of convex functions is convex again. So if we have now f1 and f2 convex, then we can use then we know, I think this was proposition 5.3, that APF1 plus APF2 is also convex, and now we know that the infimal convolution at some point x can be equally written as the infimum over all values alpha, such that x and alpha is in the epigraph of f1 plus the epigraph of f2. This is just actually the definition. It's written just differently for the for the inf-convolution. So this alpha is then always below the graph. So yeah, it's just write down the definition of the inf-convolution again, and you'll see that this is exactly the same thing. And now we can invoke our theorem 272. Implies that the left-hand side is the convex function, because it's exactly of that form which we considered in theorem 7.2. Okay. Yeah, and we are more or less at halftime, but I've covered already quite some ground here. So there's again time for a short break, and in this short break there will be more dad jokes, and see you in 2 minutes. Welcome back for the second part of the lecture. So, examples on inf-convolutions, and unfortunately inf-convolutions are also not always that nice. So they stay convex, but apart from that it's more complicated. So here's an example. 7, okay. We do it on the real line with convex functions, and one of them is, so that's the first example, one of them is f1 of x is times p of x for some real number p, and the second function is the exponential function. So both are convex. That one's linear and that one's convex because the second derivative is positive, for example, or the first derivative is increasing. So both are proper CVX and even continuous, not only lower semi-continuous, but continuous. Let's consider the inf-convolution. f1 inf-convolved with f2 at some point u. So what we need to do is to find the infimum value of decomposition x. I divided only over x. So here it's p of x. This is f1 of x, and then we have plus exp of u minus x. So this, you have to find this infimum, and you have to do things like this pretty often in the future. So let's see how this goes. So infimum over x, and we use standard calculus, taking the derivative, setting to 0, solving for x and plugging in. So taking the derivative gives you p plus, no, it's not plus actually, it's the inner derivative gives you minus x of u minus x, and this should be 0. So we need to solve that for x. So we bring that to the other side and conclude that the logarithm of p has to be equal to u minus x. So we get x is equal to u minus the log of p. So that's the point where the infimum is in this case actually assumed. Oh wait, not so quick. So here, for this to be meaningful, we had to consider p is positive. Okay, so we end up here with cases. So in the case p is positive, we get the value which we get when you plug in x over here. So this is not a very nice thing, but it's just how it is. It's p times u minus log of p, plus exp of u minus this, u minus this, u minus u goes away, plus log, it's x of log of p, it's p. So that's what we get there, and it's a pretty nice function. It's linear in u, at least, so it's a linear function. Okay, that's nice. But what happens for p, for example, equals 0? If p is 0, then this is 0, and we only need to take the infimum over the exponential function. It's shifted in mirror, but that doesn't make any difference. It's always positive, but it goes to 0. So in this case, the infimum is exactly 0. So for p equals 0, the inf-convolution is the constant function 0. But what happens for p negative? P negative, then things is different. So because this guy, so this is bounded from below by 0, but this is unbounded from below, and it goes the wrong way around. So this guy, for x to plus infinity, this guy goes to minus infinity, and this guy stays bounded from below and goes to 0 even. So in this case we get minus infinity all the time. So, and what we see, if p is negative, which doesn't seem to make a big difference, so it's a linear function after all. It's a linear function just tilted like this or like that, but it makes a difference. If it's tilted like this, if it's tilted like this, if it's tilted like this, it's minus infinity all the time. If it's tilted like that, then it's a nice linear function again. So in this case, is f1 not even proper. So there has to be something more. But also in this case, the infimum is not assumed, right? That's the big difference. Also in this case, the infium is not assumed, but here it's still nice, but here it's getting something ugly. You can also consider the epigraphs. So the epigraph of F1, let's consider only the case p equals 0, because then it's all very simple. If p equals 0, this is the constant zero function. The epigraph is everything which is positive, which means this is the real line times that, the non-negative numbers. The epigraph of F2, it's not, it's just what it is. It's the tuples x and alpha such that x of x is smaller equals alpha. And the epigraph of the inf-convolution in this case is again, because then it's a constant zero function, so it's the same thing here as there. But this is a superset of the addition of the epigraphs. And it's not the same. So if you add up the epigraphs, what you do is you take these values x and alpha, which fulfill this, and you may add any positive number right here. So it really does not change. No, it doesn't really change. So this is it's really a larger set than that one guy. Things can really go wrong in some cases, and so I blame the non-exactness right here for. In this case, it's not the non-exactness. No. Okay. Another thing which is where something else goes wrong, even lower semi-continuity can be destroyed by inf-convolution. So if you take C1 as a set, so now a two-dimensional example, y is larger equal to the exponential function of x, and C2 is the tuples x and y such that y is larger equal to the exponential function of minus x. And these are both two subsets of R2. And even both are convex and enclosed. Let's sketch them here. So we have the exponential function and exponential function of minus x. So this C1 is everything which is above the exponential function. So this here is C1, and C2 is everything which is above that one. So this here is C2. And we want to do inf-convolution, so we would consider the indicator functions. They both are convex and lower semi-continuous because of convexity and closeness over there. But what is the Minkowski sum? So what values do we get if we add some value from here and some value from there? And in fact you get any non-negative number. So we can get this point by considering something very much here and very much over there, and then adding, and you can reach that point here exactly. So this is exactly the set which looks like this. So the full upper half plane, but the open one without this axis here. So, and this is not closed. So, and this means that the inf-convolution, which is in this case the indicator function of the Minkowski sum, it's not lower semi-continuous. Okay, so that may happen. Okay. So, and this have been the important things about inf-convolution which we wanted to talk about right now. I think inf-convolutions will come back later on, because they are kind of sometimes important properties and important things to construct new convex functions from old ones. Sure, the next lecture will be about the Moreau envelope, and that's exactly an inf-convolution. Okay, but there's something else I wanted to show you, and that is that the exact same constructions, but not in the sense of not in the realm of convex analysis, are used in image processing as standard operations and building blocks. So that is now a longer example, 7-8, and these are so-called morphological operations in image processing. So morphological operations. So let's talk a little bit about imaging. An image in mathematical imaging is just a function like this, f of rg to r. So an image in the kind of sense of painting or whatever, not the painting, but a grayscale image. Grayscale. And what does that mean? It means f of x is denotes the gray value of the image at x. So x gives you a point, and usually you consider d equals 2 for plain images like photos or digital photos on your laptop. And it's just the grayscale. And there's so usually you have something like not like this, but even more restricted into the interval of 0, 1. And so, for example, A is a closed rectangle, and f of x equals 0 means f black at x, and f of x equals 1 means f is white at x, and anything in between is the gray value. So that's one way to view it. Of course, there's more things like binary images, which are black and white then, but there's also color images, and then you need to think about or know something about how colors are perceived by the human eye and how they are represented on imaging devices. And there were different ways to do that. For example, on a monitor or any display, it works by mixing RGB, so red, blue, and green colors. And with this mixture, you can kind of represent any color. So you don't need one real number, but 3 of them. And moreover, the computer only uses 256, so 2 to the 8 different values, brightness values for each of the color. So if no color is present, you get black. If all colors are pumped to the max, so to 255, you get white. And if you do something in between, you can cook up any color which the eye can perceive, more or less. In print, it's different. In print, you need 4 things. You need cyan, which is kind of a bluish, turquoise color. You need magenta, which you know from the telecom, so this is pink. And you need yellow, a very bright yellow. And but if you mix them, you will never get very dark. So you also need black. So this is a CMYK color representation, which is used in print. So if you buy a magazine in print and you look very, very closely, you'll see that all the colors are mixed by cyan, magenta, yellow, and black. So you would need 4 numbers in that case. Of course, there's even more. So sometimes transparency comes into play, or luminosity, and whatever. But anyway, so what we do it simple here, you consider gray values, just the brightness value. Yeah, I forgot. So even though the computer actually uses RGB, there are different representations of colors by hue, saturation, and value. So and hue is the color tone, saturation is the color intensity, and value is the brightness. And what is often done in color processing is that you simply focus on the brightness, and then the brightness is that kind of looks like an RGB, like a grayscale image. Okay, so that's how an image, what an image is in mathematical imaging. And for us, it's simpler to consider real-valued functions or continuous values, because then you can add and subtract as you like. And if you only have the whole numbers from 0 to 255, then of course you have to do with overflow and underflow, and what you do when you have to do the rounding and stuff. And so we just don't want to care about that. So if you now have an image and you have a subset, a B, which is in the same RD, and always think about D equals 2, a compact subset, which should be symmetric about the origin, so B equals to minus B, then you define the so-called erosion of F is then, I don't know, there are many notations here, there's no standard. They used to call it E, or epsilon of f, and that value of x is the infimum that you get if you consider f of x plus y over y in the set B. And this is now exactly No, I don't want to. This is exactly an inf-convolution of f and the indicator function of b at x. So what does that mean? So if you have an image, let's say you have some shape here, and this is now 0 and this is 1. And what do you do to so let's consider an image which is only assumes the values 0 and 1. So black here, white there. Okay, so if you have an if you had an x over here, and let's consider that b is a circle, for example. So the origin in the middle. So what you do now here is you take this point x here and add everything which you find in b. So then you consider the function values in this circle here. And you assign to the erosion of f at that point the smallest value that you can find. So in this case, everything here is 1, so it's still this pixel here stays white. And similarly, if you're inside, inside the set where the function is 0, you will find 0 in the neighborhood exclusively, so the function stays 0, of course. Interesting things now happen at the boundary. So if you're here such close to the boundary from the outside that the circle intersects this, so you have here a very slight intersection, and there the function is 0. That's the smallest thing you can find, and this pixel here gets black. So you can think of it like you kind of as soon as this blown up point by the so-called structure element b touches the set where the function is 0, so it's black, it turns these pixels black. So you can think of it so the erosion will look like something like this. Kind of you roll around, so it's, and this here will all get black. So it just extends the black regions, the erosion, so kind of erodes away the white stuff. Similarly, you have the dilation of f, delta b of f of x. It's then the supremum of y, f of x plus. So we don't have an addition like this for in convex analysis, but anyway. So note that this f does not have to be convex or anything. It just really doesn't make any difference here. It still works like before. And even the b can be, you could also use the b, the function as a b, so something like that would also make sense, but we don't do it here. Okay, before we show you pictures of this, so there are pictures in the lecture notes, you may have downloaded them already, but before I show them here in the lecture, let's say you can combine this thing out. So what happens for dilation? For dilation, it's the other way around, right? For dilation, as soon as you're touching the boundary from the inside, you are assigning white. While erosion extends, erodes away the white, the dilation erodes away the black. So this would be something like this here. So this here is now probably delta b, and this from the outside here, this is how epsilon b, the erosion, look like. So and then you may think about, what about combining the two? So what if you do first erosion? First you do erosion of something, and then after that you do dilation, and for some technical reasons we would mirror the structure element there. So what do you get? You first shrink then extend. So first for erosion you first shrink the white space and then you extend again. What do you get? Do you get back what you had? Yeah, let's think about it. What do we get back what we had? So from this picture it may look like it. So first we extend and then we shrink back. Could be, but of course not. Not, because what can happen if you would have had a small white spot, sorry. A small white spot, so we have here a large black region and a small white spot inside. So this here is all black, and you have a small white spot. If you now do the erosion with a structure element which can cover this white spot is gone totally, it's just wiped out. And if you do dilation again, it will never reappear. And also things may change its shape. This is also true. You can see kind of these erosions are always kind of round from the outside, but they make kinky from the inside. And for the dilation, it's kind of the other way around. They make a kinky outside, but they're round from the inside. So that things also change shape. But the most important property is that this operation here, it wipes away white spots. If the spots are smaller than the structure element, they are just gone. So this operation, because this is not the identity, it has a name, and this is called opening. And if you do it the other way around, first, and then I think it's still that it's b inside and minus b outside, so b of f, and then after that you erode, and then you evaluate. And this is the closing. Okay, so, and I have here somewhere, there it is, so that's the page in the lecture notes, and just magnify these images here. So, over here you have an image which is contaminated by white spots. And here in the middle you should see the erosion. So erosion erodes away the white, makes all the white spaces smaller, and you of course see that all these white spots, they are gone, but actually it's all of them, or some of them are still there. I can see in this resolution, but let's see how this. It's pretty hard to confuse it with dust. So one thing is that the white spots are gone, but you also see that the larger white structures, they are thinner. They are thinned out. But if you do now, so that's good because these white spots can be considered as noise. So for example, if this would be a black and white scan, this white spot would, for example, be annoying if you would like to do object recognition, for example. You would like to get rid of the black spots, but also now you change the shapes here a little bit. It's still readable because it's large numbers, but for smaller shapes it may be not that nice to have them distorted. But if you now erode again, dilate again, maybe I should try to extend it such that you can see both of them. So like that, for example. So here's me again, okay. And then you see that these letters are basically more or less look like before. And maybe it's even exact, but this depends on this shape of the structure element. But what you also see, it seems like that there should be a small white spot in the middle which have stayed there. So there and there white spots appeared. So that means that here's a small white spot. That means that here has to be an even smaller white spot. And you can see it here at least, so I can see it, but actually, I can see it. Nah, I don't see the white spot. It should be there somewhere, but I can see it. But what you can notice is that at that point there's a kind of larger white spot. So most of the white spots are smaller than that one. This is among the largest here, and this also gives us a hint how the structure element may have looked like. So I did not show it. It's a disk, and the radius is such that this circle is kind of, maybe it's left over, it kind of leaves a trace of one single pixel, which may be the reason why we can't see it here. Okay. So, but overall the result is pretty nice. That's very clean, and just a few pixels have been left. So of course you could also enlarge the structure element a little even more if you also want to eliminate these guys. You will run into problems if the structure element is so large that it eliminates the whole letters here, or thinner parts of the letters. And if you would have taken a different structure element, for example a rectangle or a square, then you would not get such nice round corners that you had before here. You would kind of change the ends of the set. So that's one thing which you can use morphological operations for. And I'm not really sure, but I guess this is used if you have an app which can digitize your printouts for submission. Sometimes some apps are really good at eliminating all the structures which may come spots or something which kind of distort the impression. But there's a different problem. So if you take a digital picture of something which you which you've written down black on white. If you take a picture, it's not black on white anymore, because kind of, so you always see like here. So here it's much brighter than over there, and it really depends on the lighting. So if I do the lighting over here, you see shadows, and so here you have a much darker spot than there. And this sometimes, under bad circumstances, really leads to undesired effects, such that if you now do turn the color image, which the camera usually takes, into a black and white image by thresholding or whatever, sometimes it appears that the structure mixes into the background, because this is not, the contrast is not high enough, or the lighting is very uneven. But this is also not a bad problem. It can be solved, and that is the second example in the handout. It's over here. So that's from the time when I still had to scan things. So if I wanted to discuss things with colleagues far away, so I made sketches and sent them, I scanned them and sent them via email. And so, for example, if you, and then bandwidth was even lower than today, so we want to save bandwidth and kind of compress images to black and white, because black and white is all the information in there. So I was not that, so this is a bad drawing, and this I had to use the erasure a lot, and so you see all these spots, and this it does not look really good. So, and if you do black and white conversion of this by thresholding, you will see very thick spots of black over here, and maybe this even comes black because it's so dark that it may be confused with something which I would have probably written intentionally, but no. So what you can do is, so what is the case in this drawing is that all the structure which should be there is very small. So these graphs here are small, or the letters are small, and all these smudges here, they are large. What you can do is you take a closing with a fairly large structure element, so a structure element which is larger than all the structures here. And if you do that, you eliminate all the black things, apart from them which are spread out more. So if you, the closing of that guy with a kind of large square structure element looks like that. So you see the smudge over here. It's not exactly like before. You see the shape of the square, but anyway, you see that there's a smudge over here, there's something over there, and also here and there. And if you, and then what you can do now is you subtract the background from the original. And then you end up with something like, well, it is like this. And maybe again I should try to show both at the same time. Here it is. So of course you see a little bit of distortion. So you see something here, some more structure that hasn't been there. But so this is kind of more or less nicely eliminated. So this now is really on a whiter black background than it has been before. The smudge here is kind of eliminated, but the structure, this structure here is still there actually. And this is also, and also the contrast has increased a little bit, but mainly that's a pre-processing step. If you now want to do thresholding and turn this into black and white image, you will not see things from this smudge here in the black component, because they are more or less gone. And this is probably something or something similar which also happens in apps which can digitize photographs on your smartphone. And turn them into nice black and white pictures, even if the illumination of the background is not as good as it should be. Okay, and I think that's it for today. There's more applications of morphological operations, but that would be a different lecture, and that's it for today. Okay, so thanks for listening, and we'll see you again tomorrow for the lecture on the Moreau envelope and the proximal mapping. Okay, that's it. See you.